Microfossils of primitive microbes found in rocks dating back 3.4 billion years. Fossilized remains of microbes that scientists suggest lived on the seafloor near hydrothermal vents 3.42 billion years ago have been found in South Africa. These discoveries will help scientists better understand how life arose on Earth and where it might be found elsewhere in the solar system. Microfossils of ancient methanogens have been discovered by an international team of scientists led by researchers from the University of Bologna. These are the oldest evidence of this type of life on our planet and expand the boundaries of potentially habitable environments on early Earth, as well as on other planets, such as Mars. The research results were published in the journal Science Advances. Earth's subsurface habitats encompass a vast biosphere and likely provided some of the earliest habitats for microbial life on our planet. Although the origins of life are still debated, evidence of ancient creatures provides insight into its early evolution. We present the discovery of exceptionally well-preserved microfossils, approximately 3.42 billion years old, that inhabited the hydrothermal vent system of the Barberton Greenstone Belt in South Africa. Combined with their morphological and chemical characteristics, they can be considered the oldest methanogens and/or methanotrophs that developed on volcanic substrates, the authors wrote. The Barberton Greenstone Belt is a region in South Africa, lying near the border with Eswatini, formerly Swaziland, and Mozambique, containing some of the oldest and best preserved sedimentary rocks found on the planet. After analyzing the samples, scientists found a carbon-rich outer shell of the microfossil and a chemically and structurally distinct core. We found exceptionally well-preserved microbial fossils that appear to have flourished along the walls of cavities created by warm water from hydrothermal systems several meters below the seafloor. These surface habitats, heated by volcanic activity, likely hosted some of the earliest microbial ecosystems on Earth, and this is the oldest example we have found so far, said Professor Barbara Cavalazzi, lead author of the study. These primitive life forms colonized cracks and crevices in the seafloor, where the interaction of cooler seawater with warmer, subsurface waters from deep within the Earth likely created a chemically rich soup that was suitable for life. Chemical analysis showed that the ancient microorganisms contained most of the essential elements necessary for life. The high concentrations of nickel are similar to those found in modern archaea, which live in anaerobic environments and utilize methane for metabolism. One of the great, unresolved debates is whether life arose in a warm, shallow body of water, as Darwin proposed, perhaps with the help of meteorites, or lightning strikes, or on the seafloor around hydrothermal vents. Over the years, scientists have presented studies that seem to support both theories, but the issue remains unsettled. New discoveries support the hydrothermal vent hypothesis, and may help answer some questions about how and where life first appeared on our planet, or whether such microorganisms existed even earlier in Earth's history. One of the challenges of studying the history of life around hydrothermal vents is that we don't have enough data. Every few 100 million years, the ocean floor undergoes major transformations, and although we know life exists there, its history is largely hidden. This makes the discovery by scientists from the University of Bologna of enormous significance. Charging an electric vehicle in 10 minutes. Scientists have developed a new technology. Scientists have developed a lithium-ion battery that charges at an elevated temperature, significantly increasing the speed of the entire process. Importantly, the battery doesn't degrade during this type of charging. This new technology could soon allow an electric car battery to be fully charged in just 10 minutes. Lithium-ion batteries have had a profound impact on the modern world due to their ability to store large amounts of energy in a small, compact, and reusable battery. For their contributions to this technology, a trio of scientists, John B. Goodenough, M. Stanley Whittingham, and Akira Yoshino, received the 2019 Nobel Prize in Physics. Lithium-ion batteries are excellent for consumer electronics, but in the automotive industry, they currently generate more concern than enthusiasm. One of the main barriers to the widespread adoption of electric cars is the charging time, especially when compared to the time it takes to fill a car's tank with gasoline or diesel. The key to making electric cars more attractive both commercially and in terms of utility is developing batteries that can be quickly recharged without significant loss of battery life. Professor Chaoyang Wang's team at the Electrochemical Engine Center at Pennsylvania State University appears to have achieved this. The researchers reported their research on the accelerated charging battery in the journal Joule. Perhaps soon, thanks to a new battery developed by Wang's team, electric vehicle owners will be able to fully charge their cars in just 10 minutes. This is all thanks to a new design that heats the battery to increase charging speed. We've demonstrated that it's possible to charge an electric vehicle in 10 minutes, providing it with enough energy to travel 200 to 300 miles, 300 to 450 kilometers, Wang said. We can do this while maintaining a battery life of 2,500 charge cycles. That's the equivalent of about 500,000 miles of travel, about 800,000 kilometers, he added. Fast charging of lithium-ion batteries has been possible for some time. However, the problem is that when they are charged quickly, they degrade just as quickly. This is due to the deposition of metallic lithium on the anode. During fast charging, lithium ions, moving from the positive to the negative electrode, tend to form plate-like deposits on the surface of the negative electrode. This leads to reduced cell capacity, and can also cause voltage spikes, and ultimately, battery failure. The batteries are charged and discharged at the same temperature. The researchers discovered that the lithium deposition problem could be solved by charging the battery at higher temperatures, reaching around 60 degrees Celsius. However, heating the battery adversely affects it, shortening its lifespan. In a series of experiments, the researchers determined that their design, heated for no longer than 10 minutes and then quickly cooled to ambient temperature, did not degrade. This solved the lithium deposition problem and shortened battery lifespan. During the tests, the scientists used commercially available industrial batteries. They equipped them with a micrometer-thick nickel foil structure. This allowed for heating the electrodes in less than 30 seconds, creating conditions for the rapid transfer of ions to the negative electrode without lithium deposition on its surface. They then tested the cell's performance when charged at temperatures of 40, 49, and 60 degrees Celsius. They compared this with a control battery charged at 20 degrees Celsius. They found that at 20 degrees Celsius, the battery could withstand fast charging for only 60 cycles before significant performance degradation. The best results were achieved with fast charging at 60 degrees Celsius. A battery charged in this way could withstand 2,500 charge cycles without performance degradation. This equates to about 14 years of normal vehicle use, or about 800,000 kilometers driven, the researchers calculated. It's also important to quickly cool the battery. As Wang admitted, vehicle cooling systems can be used for this. Just cooling from 60 degrees Celsius to around 25 degrees Celsius makes a huge difference in battery life. Until now, it was widely believed that lithium-ion batteries should not be operated at high temperatures due to accelerated side reactions. Our research suggests that the benefits of avoiding lithium coating of electrodes during charging at elevated temperatures with limited exposure time significantly outweigh the negative impact of exacerbating side reactions, Wang explained. The researchers claim the technology is completely scalable. The nickel foil increases the cost of each cell by just 0.47%. The research team will now aim to develop a battery that can be charged in 5 minutes without degradation.